All right, folks, welcome to the last new lesson for this course. So 6-6, today we're talking about volume of a solid of revolution. This time it's the washer method. So in 6-5, you learned about the disk method, and today we're looking at something extremely similar with just some minor differences, but they're important differences, and it's called the washer method. So to compare them, because otherwise they're very similar methods, so to compare them so that hopefully you'll understand when you would need to apply the washer method versus the disk method, first I'd like to compare the two different things. So here I have just some random graph of y equals f of x, and we're looking at the region between a and b, between f of x and y equals 0, the x-axis. So let's say this is the region that we're going to revolve around the x-axis so that we get our solid of revolution. So based on, this is what we did basically in 6-5. So remember, your radius, because we're revolving around the x-axis, your radius is going to be perpendicular to the x-axis. And so this would be sort of our sample rectangle or sample radius. This would be our r of x. And if you think about it, when this rotates around the x-axis, this is why we get that disk, right? That rectangle just sort of sweeps all the way around. Now, compare that to this situation. So once again, I've got this function, this random curve, y equals f of x from a to b, but I also have the second line, or second curve, y equals g of x. And so the region that we're going to revolve around the x-axis this time is this region up here in pink instead. So again, that means if I were to take my sample rectangle perpendicular to the x-axis, because we're revolving around a horizontal axis. So if I were to take that sample rectangle, now if that one gets revolved, think about what's going to happen now. So it's going to look something like this. In other words, it's going to look kind of like a ring that has a hole in the middle. And so for anyone who's done anything with like wood shop or hardware kind of stuff, this is known as a washer as far as tools go. But now, let's kind of think about what we did yesterday. So remember in the previous lesson, where the formula came from was the fact that we were really dealing with cylinders. They were very, very short cylinders. And so that's why we needed to know the radius and then the height, because the volume was just going to be pi r squared times the height. But in this situation, now what we're looking at is still a cylinder, so it's still like a disk, except now it actually has a hole cut out of it. And so think about how you would find the volume of this particular solid. Well, really, what we have is, now we're looking sort of bird's eye view, we have an entire cylinder. So let's say that the radius from the center to the outside of the big cylinder, I'm going to call that capital R, so it's sort of the bigger radius. So that means the volume of that outer cylinder is going to be pi times the big radius squared times the height. But now the hole is actually another cylinder that's getting cut out of it. So that right there would represent this other cylinder that's getting cut out of it. And that cylinder, I'm going to say that its radius is little r. So in the picture, this right here would be little r. And so what we're really doing then is now we have to subtract the volume of that smaller cylinder that we're cutting out of the middle. Well, and that's going to be pi times little r squared times the same height. And so now if you look, both of them contain a pi, both of them contain an h, so I can now factor out the pi and the h to look like this, pi times big R squared minus little r squared times the height. And so now if you remember, the height is really side to side in our washer, so that's really going to be our delta x. And then the radius, again, that's just going to be our function, but now that radius is going to be the full distance from the axis that we're revolving around to the farthest boundary of the region. Sorry, I should do color coordinating here. So again, we're going from the axis to the farthest boundary of the region, that's going to be your big R. And then from the axis to the closer boundary, that's going to be your little r. Now notice, I did not do top curve minus bottom curve. I was not trying to measure this distance here. We're actually trying to find two different radii. We're trying to find the bigger radii and again, the smaller radii. Notice that each radius has to come from the center. That's why both times you saw me measuring from the axis that we were revolving around. Okay, so finally, keeping all of this in mind, if I were to take this equation right here, remembering that h is really going to become our delta x or our dx, what that now gives us is for the washer method, the volume is going to be pi times the integral from a to b of the expression for the big radius squared minus the expression for the little radius squared dx. And this right here becomes our formula for this washer method. Okay, so again, looking back at the original pictures that I drew, to make sure you understand when you're doing a disc versus a washer, notice that for the disc method, that the axis that we were revolving around was actually one of the boundaries of the region, versus this washer method, where the axis that we were revolving around was not one of the boundaries of the region. In other words, notice that there was some blank space between the region and the axis. If there's any empty space between the region and the axis, that empty space also gets revolved as well, and that's what's creating this washer. That's what's creating the hole in the middle, is that we're rotating this empty space. Okay, so as you go through your assignments, some of the problems will be the disc method from the previous lesson, and some of them will be the washer method from this lesson, and you need to make sure you understand which is which, and it's going to depend on how the region compares to the axis that you're revolving around. Okay, so let's look at some examples. All right, so our first example says, set up and evaluate the integral that gives the volume of the solid formed by revolving the region bounded by y equals 1/2 x squared and y equals x about the x-axis. All right, so let's go ahead and first take a look at what this region is. So we're going to sketch the graphs here. Okay, so the region looks like this. We've got y equals 1/2 x squared, so that's just our parabola, and it's been vertically compressed. So, and then y equals x is, of course, just this line at the 45-degree angle. And so the region is right here, enclosed by those two functions. So we are revolving about the x-axis. And so once again, notice that the axis or the line that we're revolving around is not one of the boundaries of this region. Yes, it touches the region right here at this point, but again, if there's any empty space between the region and the axis that you're revolving around, you are going to create this washer. You're going to create that disc with the hole in it. And again, if you imagine what this is going to look like if you were to revolve it, let's see, it's going to look something like this. Okay, so that's why we are going to end up with the cross section that is a washer. Okay, so that means we need to be able to correctly identify and draw the big radius and the little radius. So here's what I want you to do every time. So to draw your big radius, you start with your pen or pencil on the axis that you're revolving around and anywhere lined up with the region. So I'm just going to go randomly right here. And then we're going to go perpendicular until you get to the farthest boundary of the region, which in this case is here. So that right there is our big R. And then for your small r, same thing. You're going to start on the axis, and you're going to go perpendicular to the axis until you get to the closer boundary of the region. which in this case is right here. So now, to write your expression for the big radius, now we're doing what you've always done before, top minus the bottom. So for this big radius in red, the equation of the top is just x minus the equation on the bottom is y equals 0, so x minus 0. So that means our big R here is just x. Now for little r, same idea. We're going to do the upper curve minus the lower curve. So the upper curve is y equals half x squared. So 1/2 x squared minus 0, which just becomes 1/2 x squared. So those are the expressions we're going to use for big R and little r. So now we can set up our volume. So volume equals pi times the integral from, now we didn't actually find our limits yet. Clearly they're going to both start at 0. And from the graph it does appear that this is x equals 2, but let's just make sure. So remember, if I set these two equations equal to each other, it is quadratic, so I'm going to subtract the x from the other side. And then we can factor out an x. So we do get x equals 0 and x equals 2. So sure enough, the upper limit is 2. All right, so now remember it's big R squared, so that's going to be x squared minus little r squared, and that's going to be 1/2 x squared squared dx. So this right here is the integral that we would use that gives the volume of the solid formed by revolving this region about the x-axis. So now let's go ahead and evaluate this. Now my recommendation is, I don't want you to get out of practice of evaluating definite integrals by hand, so I would recommend doing some of the problems by hand and some of them with the calculator, because both of those skills are going to be important. So for this one, let's go ahead and do it by hand. So I get volume equals pi times the integral from 0 to 2 of, let's go ahead and expand this. So this is x squared minus 1/4 x to the 4th, or I'm just going to write this as x to the 4th over 4, either way. So now we can integrate. So I have pi times, so this is going to be x cubed over 3 minus x to the 5th over 20 from 0 to 2. All right, so now let's evaluate. So I have pi times, so this is going to become 8/3 minus 32/20 minus a 0 minus a 0. Now 32/20, both of those do divide by a 2, so this is really 16/10. Oh, actually both of them divide by a 4, so this is really 8/5. So I have volume equals pi times 8/3 minus 8/5. And then let's see, if we get a common denominator, this is going to be 40 minus 24/15, which finally gives me 16 pi over 15. And that right there would be the volume of the solid formed if we were to revolve this region about the x-axis. Okay, so let's do another example here, but for this one we're not even going to evaluate. We're just going to focus on setting up that integral, just making sure that we understand how to correctly set it up. So let's first, again, take a look at what this region is. So we're talking about the integral that would give the volume of the solid formed by revolving the region bounded by y equals the square root of x and y equals x squared about the line y equals 2. So let's, again, take a look at what this is talking about. Okay, so this time the region looks like this. It's this tiny little sliver down here in blue. So we have y equals the square root of x. We have our parabola y equals x squared. But again, this time we're revolving around this line y equals 2. Now it's still a horizontal line, so that means we are still going to be perpendicular to the x-axis. So everything is still supposed to be in terms of x. So that hasn't changed. But again, remember we are going to try to find our expressions for the big radius and the little radius. So once again, to reiterate, start by putting your pencil or pen on the axis that you're revolving around. Notice that this time the axis is actually above the region, and sometimes that'll happen. It's not a big deal. So I'm starting there, and I'm going to draw perpendicular to that until I get to the farthest boundary from the axis. So that right there is my big R. And then for the little r, same thing. Start on the axis that you're revolving around and draw perpendicular until you hit this closer boundary of the region. So that right there is my little r. Okay, so now for big R of x, again, we're doing upper curve minus lower curve, or greater curve minus lesser curve. Now remember, the equation of the top is y equals 2. So we're starting with 2 minus, and then the bottom curve is x squared. So my expression for big R of x is 2 minus x squared. For little r of x, same thing. We're going to go top minus the bottom. So the equation at the top is y equals 2. The equation at the bottom is square root of x. So these are the expressions we're going to use for our integral. And in terms of our limits, clearly we're going from 0, and hopefully you recognize that this is happening at 1. If I were to set x squared equal to the square root of x, if I subtract the square root of x, no, you know what, let's not do that. Let's actually square both sides first. I get x to the 4th equals x. Now I get x to the 4th minus x equals 0. I could factor out an x. I get x cubed minus 1. So we do get x equals 0 and x equals positive 1. Okay, so that means now we can write out our integral. Actually, go ahead and pause right here and see if you can write it out first. So go ahead and pause. Okay, so hopefully you had volume equals pi times the integral from 0 to 1 of, now be very careful here, it should be 2 minus x squared squared. And by the way, I use brackets. You can use parentheses. It doesn't really matter. Minus 2 minus the square root of x squared dx. And this should be your integral that would give the volume if we were to revolve this little blue region around y equals 2. All right, so this time let's go ahead and use a calculator to evaluate that. Okay, so let's go ahead and type this in. Again, don't forget about the pi. That's still probably one of the most common mistakes people are going to make, is forgetting to multiply by pi. So we have pi times, now again, the integral, so math 9 from 0 to 1 of. Now again, be very careful here. Make sure you're paying close attention to when you need parentheses, things like that. So first remember we have the quantity of 2 minus x squared. So I need parentheses again. 2 minus x squared, close parentheses, squared. Remember, don't forget, it's a big radius squared, minus small radius. So again, it's 2 minus the square root of x, move out of the radical, close the parentheses, squared, and then that's dx. And we get approximately 3.246. 3.246. I do recognize that this did say just to set up but do not evaluate, but I did want to make sure that I demonstrated at least once typing that into the calculator, because again, you do want to make sure that you're very careful with your use of the grouping symbols. Remember that when you are using your calculator for an integral, after you do your integral from a to b, remember it already starts parentheses around your integrand. So any additional grouping within that, you do need to make sure you use other parentheses. So in other words, don't try to use the parentheses that they've started you with for any other grouping, okay? If you need to add parentheses, add them in beyond the ones that are already there on your calculator. Okay, let's try just another example here. All right, so this time we're going to find the volume of the solid generated by revolving the region bounded by x equals the square root of y, the y-axis, and y equals 4, about the line x equals 4. So once again, we're going to start by trying to find what that region looks like. All right, so the region looks like this. Now, x equals the square root of y. If you were having trouble figuring out how to graph that, remember that if you were to square both sides, you would actually get x squared equals y, or in other words, y equals x squared. So really, this is just the parabola, but it's the right side only, because really we're just dealing with positive x values. Okay, so that's how we get that curve there. Oops, I didn't label it. So again, this is x equals the square root of y. But again, notice that this time we are revolving around x equals 4. We are revolving around a vertical axis. So remember that that means that our radius or radii have to be perpendicular to the y-axis. So this time, our big radius and our little radius, and this is a washer because we have all this empty space between the axis that we're revolving around and the region itself. So the big radius and the little radius have to go horizontally now. They're perpendicular to the y-axis. Okay, so let's draw the big radius. It's the same story. So remember before, we were always starting on the axis that we were revolving around, and then we're going to go perpendicular to that axis until we get to the farther boundary. So same thing here. I'm starting on the axis that I'm revolving around. I'm going to go perpendicular to that until I get to the farthest boundary of the region. So that right there is my big R. Similarly, for the small radius, starting on the axis that we're revolving around, and then drawing until I get to the closer boundary of the region. So that green line right there is my little radius. So now, to find our expressions for the radius, or the radii, remember this is going to be big R of y. Remember now this is in terms of y because we're perpendicular to the y-axis. So that means for my expression, I need to compare the x values. So what's the equation of the rightmost? Well, that's x equals 4. So 4 minus, now what's the equation on the left end? Well, this is actually the y-axis, which is x equals 0. So really, that big radius is actually going to be a constant of 4. And if you look at it, it should make sense. No matter where I am across from this region, the big radius is always just measuring this entire thing. In other words, if I were to revolve this, let me redraw this real quick over here. If I were to revolve this region about that line, the outer part is actually going to look very much like a normal cylinder. It's just that the inside has sort of a flared bottom for that opening. Okay, so the big radius is just 4. For the little radius, so little r of y, same idea. What's the equation on the right? Well, that's x equals 4. Minus, what's the equation on the left? That's x equals the square root of y. So that's my expression for little r of y. And then remember, for the limits, we have to look at the y values because everything is in terms of y. The lowest y value is 0. The highest y value is y equals 4. So that means our volume will be pi times the integral from 0 to 4, again it's the y values, of big R, so that's 4 squared, minus little r squared, so 4 minus the square root of y squared, dy. And that right there is our integral that would give the volume of the solid if we were to revolve that region around x equals 4. So let's go ahead and type that into the calculator, or you go ahead and type that into the calculator and see what you get. And I believe you should have gotten approximately 108.909. Okay, so this is the washer method, and I hope you realize that it's got a lot of similarities to the disk method. Again, the key word being revolve in the instructions. That's how you know we're dealing with either a disk or a washer. And in this case, you knew that it was a washer because the region is here, but the axis that we're revolving around is way over here. There was all this blank empty space that was going to also get revolved, and that's what's causing that opening, that hole in the middle of the washer. Okay, so as you go through the assignment, as I said before, make sure that you're taking a look at what the region looks like, because some of the problems will be the disk method and some of them will be the washer method. Now, worst case scenario, if you just approach everything as a washer, then it just means that your small radius is going to be a 0. And that's not awful, but it's kind of a waste of your time. Okay, but again, you will know that it's the disk method because the axis or the line that you're revolving around would actually be one of the boundaries of your region. You'll know that it's a washer if the line you're revolving around is not one of the boundaries. You've got any empty space in between. All right, congratulations making it through the final lesson, and good luck.